Okay, I need to I just need to find out the last slide that we were on. Let's just start from the beginning. So last time we covered counting, and we learned a bunch of tricks in order to count stuff, like normal counting, this stuff, finding the number of terms in a list, where we found the rule and we solved the problem using the rule. We solved a bunch of other hard problems, counting with addition and subtraction. We used Venn diagrams. We found out how to use the Venn diagrams in order to sort everything. We found out how to multiply stuff together to find the number of possibilities for a problem. We found stuff like this, and that's all I think we covered in the last week. So today I'm going to be starting with permutations. So permutations is something that you're going to hate doing. I hate permutations too, but this shows up a lot on competitive math competitions, and you should probably learn it if you want to be able to succeed. So here we go. Many math competitions will have problems where you have a limited number of elements inside of a list and you can't use anything more than once. So how many ways can I arrange 4 different books on a shelf? So we have 4 different books. And so think of it this way, we have like a shelf and we have 4 different places where we can put books. Now we need to find the number of possibilities for each place. So I have 4 books and I can only use each book once. So it's not like we can use one multiple times. So here we start with the first position. So our first position is 1, and since we have 4 different books to choose from, we can just start with 4. And now we have our first book here. And for the second position, we only have 3 books left since we already took one for position 1. So we multiply by 3 since there are 3 possibilities for the second book. And for the third, we just do the same thing. We only have 2 books left to choose from, so we multiply by 2. And the last one, we have 1 left, so just do this. So 4 times 3 times 2 times 1 means 24 ways to arrange 4 different books on a shelf. So you'll see this type of problem a lot on like math competitions and stuff. You'll have a limited number of things you can choose, and you have to multiply it like this, do like n times n minus 1 and all that stuff. So let me just clear my screen. Let's move to the next slide. So here are some basic permutations practice problems. So I want you guys to do these, and if you have any questions, you can private message me.
The chat's off.
Oh, sorry, let me just turn that.
Okay, there's no chat. Gone. The chat is gone. The chat is very gone here.
Let me just.
Yeah,
I don't know where that is, so let me just
There's only participant share screen, record, and reactions. There's no chat.
No chat, and leave meeting, and mute, and stop video. No chat.
Walk meeting. Hold on, I'm still trying to find it. Where is the chat button? Let me just search it up. While I look for how to do it, can you do the problems?
I'm already done. I'm writing them down.
I just need to find out how to enable chat.
When you say like how many possible orders of 3 cows can you choose, do you mean like which 3 cows? Like which 3 cows, or like how many orders there are going to be?
Like how many orders? So order matters here. You can't just choose 3 of them.
Wait, can you reuse cows?
No.
Obviously not.
Okay, then I got the right answer. Okay.
Okay.
Is the answer for the first
I think this
demonstration code?
says that I have to end the meeting in order to I have to end the meeting in order to enable chat, so I'll just end the meeting.
Just shout out the answers.
What? No, don't end the meeting.
So I have to end the meeting to enable chat, so I'll end it and then I'll start it again and you guys can join back.
Okay.
Okay. Bye.
Bye.
Well, why is it? Okay, let me just stop share.
Oh, there's still no chat.
Oh, I see it now. Can you see this?
Could you write
Just-
something in it?
Yeah, I just sent a chat. You guys see it?
No, there's no
Wait, I have
chat
no
box.
chat.
There's literally no chat.
Yeah, there's no chat button.
That's weird. How do you guys see it then?
We don't.
So at the bottom,
Don't
it just
We
says
don't.
it has the mic, it has the video, it has the participants, it has the share screen, the record, the reactions, and then the leave button. There's no chat.
Oh, that's really weird.
Yeah, it's supposed to go like mute or unmute, stop video, participant share screen, record. And there's supposed to be a chat in there and reactions and leave.
I
Maybe we'll have to leave and rejoin again.
I can see chat. And there's reactions too.
You guys should probably
everyone
leave
check
and
this.
join again if that works.
Okay, hold on, I'm gonna read
Okay.
it.
Now we can see chat.
Okay, that's good.
I already covered.
Wait, but chat's disabled.
Disabled.
Yep.
I think I can enable it in here.
After you do that, can you continue sharing screen?
Chat.
I think I fixed it. Let me just.
It's working.
Good. Oh, oops. Okay, so let's go over these problems. So here first we have a farmer has 15 cows and chooses to milk 3 random cows. How many possible orders of 3 cows can he choose? So this is not like the earlier problems where we just chose 3 of them. In this one, order actually counts. You have to like if you have A, B, and C, C, B, and A would be different. So here, what we do is we set up 3 positions. So 1, 2, and 3. Now for the first position, we can have 15 cows to choose from. So we just write in 15. And for the second position, we only have 14 cows to choose from since we already used one in position 1. So times 14. And in the third one, we have 13 cows to choose from since we already used 2 of them. So yeah, we just have 15 times 14 times 13, and we multiply these together, and we get 2,730. Wait, yeah. Now for the second one, we have John has 8 different blocks, and which he wants to stack into a tower using all of these blocks. How many towers can he make? So here we go. So for this one, we have 8 blocks and we have 8 positions since we can insert. We have to use all of them. So we have 8 positions to place blocks in. So here we can set up all the positions so we can. Wait, hold on. Okay, I'll go over the first thing again. So basically these types of problems, you want to set up 3 positions. Now, since we have 15 cows, we have 15 possible cows to choose from. So I can choose a random one, and that'll give me 15 possibilities for the first one. And for the second one, we already used 1 cow, so there are only 14 possibilities. And for the third one, we already used 2 of them in positions 1 and 2. So we only have 13 possibilities left. So we multiply these together and we get 2,730. All right, let's go over the second one now. So here we go. So let's just draw like a block tower or something. I can't fit that all, I'll just draw 2 up here. So we have positions 1, 2, 3, 4, 5, 6, 7, 8. Now for the one on the for the first position, we have 8 different blocks to choose from. And so what you do is you just have 8 possibilities, so we can just write 8 for this first slot. And for the second one, we only have 7 since we already used one. So times 7. And then we just do the same thing. So we have times 6, times 5, times 4, times 3, times 2, blah, blah, blah. And if you know stuff, you'll know that this is 8 factorial. So that's like a good trick. If you have like the same number of positions as you do like objects, then you can just write it in the factorial term and then solve it. CC means closed captions. So if you just multiply it all together, you'll get 40,320. Yeah, so that's the answer for the second one. Now let's move on. So here is the permutations formula. So basically what n is the number of things you can have. So like in the cows problem, it would be 15. Since like, let's look at the cows problem again. It would be 15 cows and 15 possibilities to choose from. And that is the number of possible elements. And R is the number you're going to choose. So like in the cows problem, that was 3, since we chose 3 cows. So basically another way you could solve that is like 15 factorial over 15 minus 12 factorial. Wait, actually 15 minus 3 factorial, which gave us 15 over 12 factorial, and then you could just divide it and solve it. So let's just move on here. So I'll do the first one. So a lottery is ran where 15 balls, each numbered 1 to 15, are placed in a bin and 3 balls are drawn one at a time. What is the possibility of someone winning the lottery if they submit one ticket with 3 random numbers on it? So here we just have 15. So we need to find the number of possible elements and the number of elements we're going to choose. So let's go here. The number of possible elements, we have 15 balls we can choose from, so it'll be 15. factorial. And now we just find the number of possible elements we can choose from, which is 3, since there are 3 random numbers. Yeah, this is the same as the cal problem. I'm just showing you guys the formula, which is 15 over 12 factorial. And if you know your factorials, you'll know it is 15 times 14 times 13 times 12, so on, over 12 times 11 times 10 times 9, blah, blah, blah. Now, if you guys know this trick, you'll solve these a lot easier. So basically, there's a trick for this, and since you don't have to multiply out all of the factorial, since you know that the later part after 12 is going to be the same as the divisor. So this is basically like 15 times 14 times 13 times 12 factorial over 12 factorial. So you can just cancel this out. And so you'll just have 15 times 14 times 13, which is 2,730, just like the last thing. Now the second problem is basically the same thing. I want to choose 2 books from a shelf containing 92 books. How many possible combinations of books can I choose? So here, what we want to do is we can use the formula again. So let's go. 92 factorial over 92 minus 2 factorial. Since 92 is the number of books and 2 is the number we're going to choose. And then we are just left with 92 factorial over 90 factorial, which is 92 times 91, if you use that trick that we said earlier, and that is equal to 8,372. We don't divide it by 2 since order matters, and like A and B, if we choose A first and then B later, it won't be the same. Hold on, I didn't word that right, sorry. I was intending to make it so that order matters, but I guess you'd be right too if you divide it by 2. Well, anyway, let's just move on. Important note. So here, don't use the formula every time. There are some cases, like in the ones where you don't have many to choose from, you don't have to choose that many. Like if your number is like 3 or 2 or 4 or a really small number, you can just do the first method that I showed you, which was like just write it out yourself and then solve it. You don't have to do the formula all the time. And usually, in math competitions, the earlier problems will not require the formula, while in the later problems, it's better to use the formula instead of using brute force to solve a problem. Also, I worded that other problem badly, and it's okay if you thought that order didn't matter for that one, but I was teaching permutations, so I could have like worded it better. So I'm sorry about that. So now we're going to find casework, which I also really hate casework, but it's also really useful if you want to get into math competitions. So in casework, what? Oh, never mind. So
I'm terrible at casework. I'm terrible at it.
oh yeah, well, I suck at casework too.
Me too.
So in casework, we have to break up a problem into several cases. So basically, we multiply some things together and all that stuff, and then solve it. So in many counting problems, we can solve it using casework when nothing else is possible. So this is an absolute value problem. Like if you don't know what absolute value is, it's like this thing where whatever you have inside of the 2 lines, it's always going to come out positive. So if you have like the absolute value of -3, it's going to be 3. And if you have the absolute value of 2, it's still 2. So it has to be positive. So this problem has two different cases. So if, let's just say we have two different cases. In one case, 2x plus 3 is positive, which means that absolute value doesn't affect it at all. 2x plus 3 equals 3 minus x. And for the second case, the number inside of the two lines is negative, which means that it's going to be turned negative in order to be made positive. So negative 2x plus 3 equals 3 minus x. So let's solve the first case first. 2x plus 3 equals 3 minus x. So we can solve this pretty easily. 3x equals 0, x equals 0. So that is one case. And for the second case, we have negative 2x minus 3 equals 3 minus x. We can also solve this one. Negative x equals 6. And I think x is -6. So yeah, there are two answers for this one. X equals 0, -6. So that's the basic thing of casework. I think this is a practice problem, and I'll give you guys some time to do it. If you have any questions, you can private chat me. All right, so I think I gave you enough time to do this. So here, let's go. On the island of Mumble, the alphabet has only 5 letters, and each word has no more than 3 letters in it, which means it can have either 1 letter, 2 letters, or 3 letters. So how many words are possible? So there are 3 cases in this problem. Case 1, we have 1 letter. Case 2, we have 2 letters. In case 3, we have 3 letters. So for the one letter, we just solve it like we would solve a normal permutations problem. We just have 5. Since there's only 5 letters, like let's say A, B, C, D, and E, there would be 5 words from that, which would be A, B, C, D, and E. So like just like that. And for number 2, we have 2 letters. So here we would multiply this. And since we can reuse letters, we just do 5 times 5 since there are 2 spots. And this would be 25. 25 2-letter words.
Wait, shouldn't it be 5 to the 3rd power, not 5 squared?
No, I'm doing
Because
casework.
no more.
I'm counting the 2-letter words now. So, and next for number 3, we have the 3-letter words. So now we can do 5 to the power of 3 equals 125. So we have 5 1-letter words, we have 25 2-letter words and 125 3-letter words. We add all the words together and we get 155. That's the answer for how many words are in the language. So here's another practice problem. I'll give you like 3 or 4 minutes to do this one. All right, I think I gave you enough time to do this one, so let's solve it now. So how many pairs of positive integers satisfy m cubed plus n is 17? So this is positive integers. I don't think zero is not a positive integer. It's just 0. So here we have several different cases. So when we look at this casework problem, we want to look at the m to the power of 3, since we know there's only a few positive integers that are, when they're cubed, they're less than 17. Oh, let's start here. So there are a few cases. First, let's just do the case of m equals 1. So 1, right? And 1 cubed is still 1. And then that means n would equal 16. So we have 116 here. And now we have the second case, which is m cubed, which is m is 2. So m cubed would be 8. And then n would be 9, which equals 17 as well. So 8 and 9. And 3 doesn't work since when it's cubed, it's larger than 17, and you need 2 positive integers, so you can't use that. So then that means the answer would be 2 pairs. All right, so let's move on to the next thing. So now we have complementary counting. This means the technique of counting what we don't want to count instead of what we do want to count. Sometimes it's better to count what's not included in the problem instead of what is included. And whenever it's easy to count what we don't want to count in the problem, what's excluded, you should just use complementary counting instead. So how many 3-digit numbers are not multiples of 7? So when we look at this problem, we know it's going to be really hard to count every single number that's not a multiple of 7. What we do want to do though is we want to count the multiples of 7 so we can subtract them later. So here, let's count the multiples of 7 as 3-digit numbers. So the smallest multiple of 7 that is a 3-digit number is 105. And the largest multiple of 7 that's not a 3-digit number, I think it's like 994. So these are the multiples of 7. And now we just divide it by 7. So we have 15 to 142. And we just find the number of integers that are in there. And 128. So there are 128 multiples of 7 that are 3-digit numbers. So now we know the total number of 3-digit numbers. It's going to be 999 minus 100 plus 1 equals, let me just move this. This thing's in the way. Let me just write somewhere else. Equals 900. So what we have now is we have the total number of 3-digit integers, and we have the number of 3-digit numbers that are multiples of 7. So in complementary counting, we've already counted what we don't want to count. So now we just subtract it from the total number of stuff. So 900 minus 128 equals 772. So that's the answer. That's the number of things that are not multiples of 7. All right, let me just move on to the next slide. So this is an example of complementary counting. So here, the Smith family has 4 sons and 3 daughters. In how many ways can they be seated in a row of 7 chairs? So at least 2 boys are next to each other. So this is going to be easier when we count stuff that we don't want to count. So here, we're going to place these people so that none of the boys are next to each other, which is what we don't want to count. So we have a son, I'll draw it as a square, a daughter is going to be a circle, and here, so now this is what we don't want to count since none of the boys are next to each other. So now we need to find the number of possibilities where the arrangement is like this. And so there would be 4 possible boys here, 3 possible girls, 3 possible boys, 2 possible girls, 2 possible boys, and then just 1 for each. So we multiply these all together and we will get 36 or something. We would get 144 possible arrangements for the stuff that we don't want to count. Now we find the total number of total possibilities that include what we do want to count and what we don't want to count. So that would be the factorial of 7, since these are the total number of ways we can just randomly put kids into different spots. And that's just 7 times 6 times 5 times 4 times 3 times 2 times 1, which when you multiply it, it should be 5,040. So now we just subtract 144 from 5,040, and we get 4,896. So yeah, this is the answer for this problem.
I have a question.
What's your question?
Like the problem you just did, is that going to be like on AMC 12s or AMC 10s?
I'd say it's like, it's like problem number like 12 or so, like 10 to 20 on the AMC 10. So yeah, you might want to watch out for this.
Okay.
All right, so here's 2 practice problems. So I want to give you guys a few minutes to do these practice problems, and then if you have any questions, you can private message me.
I don't get the second problem.
Don't worry, we're gonna.
I agree with Alvin. It doesn't even make sense.
All right, so let me explain the second question real quick. So basically, it means if you're not allowed to sit a group of 3 people all next to each other, so like you can't sit them like all directly next to each other. You can sit 2 of them next to each other, but you can't have the 3rd person there. You just can't have them all like right next to each other.
Basically, COVID-19 situation.
Yeah.
What? Wait, but you have to sit together. So how do you like? What?
Like if you have a group of 3 friends and you can't have all the friends right next to each other. You can have 2 of them next to each other, but you can't have all 3 of them.
Wait, so basically you two sit together and one's like,
No,
over
that's
there.
possible, but that's not like the entire problem. So like the whole problem is how many ways can you do it so they can't, you can't have all three of them being next to each other. I gave you guys enough time. So let's just do the first and the second problem. I know a lot of you guys were confused with the second problem, but don't worry, I'll still explain to you how to do it. So first one, how many three-digit numbers have at least 1 0 and 1 1? So here we want to count what we don't want to count. So here we just count, we can like rewrite the problem as how many three-digit numbers have no zeros or ones. So basically it would just be 8 times 8 times 8, since you can't have any zeros or ones. This is what we're counting. We're counting what we don't want to count here. This is complementary counting. And since there are only 8 possible digits for each slot, 2, 3, 4, 5, 6, 7, 8, 9, and then that would be this is 64 times 8, which is 512. And this is the number of three-digit numbers that have no zeros or ones. So now what we want to do is we want to find the total number that has both what we want to count and what we don't want to count, and then subtract 512 from that. So we know the number of three-digit numbers is 900 minus 512, since we subtract that, and we get 388, which is the number of three-digit numbers that have at least 1 0 and 1 1. Now for the second one, this one was pretty confusing. In how many ways can 7 people sit next to each other if we are not allowed to sit a group of 3 people next to each other? So this is complementary counting. So we are going to count the number of possible arrangements where we have all 3 people sitting next to each other. So we can like put all the 3 people into one like super group of count them all as one person and then break them up later. So here we just have like 5 people and 1 person. So let me just draw all the possible things you can do. Let me just draw it as a big circle. This is the super person, aka the 3 people. Let me just draw the 3 people. So you just do this. And you can just draw the last 2 and you'll find that there are 5 different possibilities where you can have the 3 people sitting right next to each other. But in this case, you also need to calculate the different ways all 3 people can sit right next to each other. So that would be 3 factorial, which is 6. So 5 times 6 equals 30 different ways where you can have the 3 people all sitting next to each other. So yeah, so basically, yeah, so this problem, this is complementary counting. So we're trying to find the number of ways we can have all 3 people sitting next to each other. So since all these 3 people are in a group, so these 3 people are all in a group, so we can just count them as 1 person right now. So if you sit this, no, these 3 people, yeah, there are 7 people, but the problem says that there are 3 people that are not allowed to sit next to each other. So we're just doing complementary counting, which means that we're trying to find the number of ways we can have all 3 people sitting next to each other. So I'll place them in a group here, and then I'm going to count them as 1 person. So I'll just draw them like this. So here, 1, 2, 3. And these 4 people are just random people. They don't really matter. And since these 3 people are in the group, I'm just putting them all as 1 person. And I'll just draw the possibilities. You can put these things together. And in total, there are 5 different possible ways where we can just have, there are 5 different ways where we can put all 3 people together, but now we need to multiply the number of ways we can sit these 3 friends and the number of ways we can sit the 4 other people. So when we calculate the 3 friends, we will get 3 factorial. And when we calculate the 4 other random people, we'll get 4 factorial. So it'll end up being 4 times 3 times 2 times 1 times 3 times 2 times 1 times 5. So now I'm going to multiply these all together, and I'm going to get I think I'm going to get like 720 or something. But I can't. Yeah, 720. So this is the 4 factorial is the other people, the number of ways we can sit the other 4 people. So this is the number of ways we can have them all sitting next to each other. And now we just do 7 factorial to find the total number, which is 7 times 6 times 5 times 4 times 3 times 2 times 1. And if we do this, we'll get 5040. We just subtract 720 from 5040, 4,320. All right, here now we have our last topic is constructive counting. So in some problems, it's not immediately clear how to count it and which method of counting you should use. But if you think about how you're going to construct it, you can find a way to count them. Usually you want to find the number of possibilities for each digit or thing. So how many 3-digit numbers have exactly 1 0? So we can't really do like complementary or casework here. Well, this is kind of casework, but it's like a different kind of casework here. So let's just do this one. So first we need to think about where we can place the 0. So you can't place it in the leftmost digit because you can't have the 0 as the first digit inside of the 3-digit number. So we can put it in either the second or the third digits. So basically we have 2 different places where we can put the 0. So we write 2 here. And then we calculate the number of digits we calculate the number of digits the first digit can have, which is going to be 9. So times 9 here. And then we calculate the number of possibilities the other digit that's not the 0 can have, which is also 9. So we get 162. So, oh yeah, here's an example. How many sequences with 6 terms can we form where you can choose from 7 numbers, but no 2 numbers next to each other can be the same? This one is sort of different from the first one. So what we're going to be doing is finding the possibilities for each digit. So we can draw these digits as x's. We only have 6 of them. Now, first digit, we can choose from any one of the 7 numbers. So 7 times the second one, we can choose from 6 of them since it can't be the same as the first one, times 6. And the third one, we also choose from 6 since it can't be the same as the last one. So times 6, and we just do the same thing times 6 times 6. And when we multiply these together, we get 54,432. So yeah, that's really what constructive counting is all about, finding the number of possibilities for each digit. So here are the final practice problems of today. I'll give you a few minutes to do these. All right, since we barely have any time left, I'm going to go over these right now. So how many 4-digit numbers have the last digit equal to the sum of the first 2 digits? So here we can have the number of possibilities. So let's just think of the sum first. So the sum can be 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so now let's just work this out like casework. So for the first case, we have 1 and 1, 0 is the only case. 2, we have 2, 0, and 1, 1. 3, we have 3, 0, 2, 1, 1, 2, and so on and so forth until I'm pretty sure we get to 9, which has 9 different sums. And so basically we just, for all the cases, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, we get 45. And now for the second one, in how many ways can 6 different gifts be given to 5 children, and each child gets 1 gift? Oh yeah, I forgot. For the third digit, can be any digit, so that would be 450, my bad. Okay, for the second one, in how many ways can 6 different gifts be given to 5 children, which each child gets at least 1 gift? We know we have 1 extra gift, which can be given to any of the 5 children. So we can just write that, we can just multiply by 5, since we have like 5 different ways we can give the extra gift to each child. And then we would just multiply this by 6 factorial. And we would just get 6 times 5 times 5 times 4. Well, since 6 factorial, since there are 6 different gifts and there are 6 spots for each gift. So yeah, if you have, yeah, stuff like that. So I'll just finish this problem first. Times 3 times 2 times 1. So 600. So then if you multiply these all together, I'm pretty sure you will get 36,000. So there are 36,000 ways to do it. All right, guys, so that's all I have for you today. I'll see you next week. See you.
Bye.
Thank you. Bye. Thank you.